everybody, so welcome back to chapter 4. In this part, we are going to be focusing on molecular compounds, specifically on our next set of learning outcomes, where we will focus on how to write the formula for a molecular compound, write the correct name, go from name to formula and formula to name. We will also talk about how to draw Lewis dot structures of molecular compounds and polyatomic ions, as well as identify what polar bonds are and discuss that. And then in our next unit, we will talk about the three-dimensional structures of molecules and how we can describe the types of intermolecular interactions that can occur between these molecules. All right, so let's go ahead and dig into molecular compounds. So again, just to remind ourselves, when we're talking about molecular compounds, now we are talking about when electrons are going to be shared between the two nuclei of atoms through a covalent bond versus when electrons are transferred between two atoms in the ionic bond. So just to reiterate, molecular compounds form when atoms of two or more nonmetals share electrons and form a covalent bond. Valence electrons are shared by nonmetal atoms in order to achieve the stability via the octet. So recall, in ionic bonding, atoms give up and take electrons in order to achieve their octet, whereas in covalent bonding, we share electrons. And when we share electrons, the two atoms that are in the covalent bond or sharing the covalent bond or sharing those electrons both can see those electrons as part of their octet. So when naming a molecular compound, typically the first nonmetal in the formula is named by its element name. The second nonmetal is named using the first syllable followed by "ide," very similar to the ionic naming. However, what's different with molecular compounds compared to ionic compounds is that we do have to indicate the number of atoms in the molecule using numerical prefixes. So, when a subscript indicates two or more atoms of an element, a prefix is shown in front of its name. So if there's one, it's mono, two di, three tri, four tetra, five penta, hexa, hepta, octa, nona, and deca. Again, this table will be given to you on the test, so you don't have to memorize that 7 means hepta, but just be able to recognize how to use the table. So for example, if we are talking about the molecular formula N2O5, where we have 2 nitrogens and 5 oxygens, we would name this molecule dinitrogen to indicate the 2 N atoms, pentoxide to represent the 5 oxygens. And again, because the second nonmetal, we replace the last syllable with "ide," pentoxide. So several compounds can be formed between the same two nonmetals, hence why we have to use the numerical prefixes in our name in order to indicate which chemical formula we are discussing. So for example, we can have both CO2, which is commonly referred to as carbon dioxide, or CO, carbon monoxide. Both of these molecules exist in nature, and if we were to follow the ionic compound naming, they would both just be carbon oxide, right? You wouldn't be able to distinguish between CO2 versus CO, even though they're two very different molecules. Now, notice when we were talking about oxide and other things like that, when the vowels O and O or A and O appear together from the nonmetals first syllable and the "ide," the first vowel is going to be omitted, right? So whether that's going to be in the prefix or in the "ide," right? So it will be dichlorine and heptaoxide. So we remove the A, heptoxide. right? So dichlorine heptoxide. If you happen to write heptoxide, I'm not going to count off, but just know that we typically will remove the A so that we don't end up with vowel overload. All right, so let's practice this a little bit. Let's name the molecule NCl3. So again, going back to our rules, when naming a molecule, the first nonmetal in the formula is named by its element name. So here it would be nitrogen. The second nonmetal is going to be named using the first syllable of the name followed by "ide." So it would be chloride. And because there's a 3 after the chloride, that indicates there are 3 chlorine atoms in this compound. Therefore, it should be nitrogen trichloride. All right, so again, step 1, name the first nonmetal by its element name, nitrogen. Step 2, name the second nonmetal by using the first syllable followed by "ide," chloride, and then add our prefixes to indicate the number of atoms as seen in the subscripts right here of the molecular formula. Because there's one nitrogen atom, we don't really need a prefix for that. You don't necessarily have to say mononitrogen. However, if you do, it's okay. The subscript 3 for the chlorine atoms is going to be shown as the prefix tri. So putting it all together, we should end up with nitrogen trichloride. All right. Now, going in reverse, we can derive the molecular formula from the name. So in the name of a molecular compound, the names of the 2 nonmetals are given along with the prefixes to indicate how many atoms of each. To write the formula from the name, use the symbol for each element and a subscript if the prefix indicates 2 or more atoms. So for example, sulfur dioxide, sulfur S, oxide O, di 2. And since the di is in front of oxide, that means we have 2 oxygens. Dinitrogen trioxide should be N2 for the dinitrogen, O3 for the trioxide. And then phosphorus pentachloride, P for the phosphorus. There's no mono or there's no di, tri or anything here, so it's just 1. You could have written monophosphorus, but again, we typically don't include the mono. Pentachloride, so 5 chlorines. All right, so let's practice this. So write the molecular formula for diphosphorus pentoxide. So again, step 1, write the syllables in order of the elements in the name. So phosphorus P, oxygen O, and then write any prefixes as subscripts following the symbol. The prefix di in diphosphorus indicates there are 2 phosphorus atoms, where the prefix penta in pentoxide indicates there are 5 oxygen atoms. Putting it all together, we should end up with P2O5. So you may ask, all right, if I'm giving a formula for some sort of compound, how do I know if it's ionic or covalent? Well, really quickly, if it's telling you penta or tri or di in the name, you can probably be safe to assume it's covalent. But if it's not telling you any sort of numerical prefix, then you may have to investigate a little bit. So a compound is usually ionic if the first element in the formula or the name is a metal, while the second is a nonmetal or a polyatomic ion. It is covalent typically if the first element is nonmetal and the second element is nonmetal, or if we are talking about a metalloid and a nonmetal. Right? So again, looking at the periodic table, if both atoms or all of the atoms in the molecule exist in the nonmetal or metalloid nonmetal category, then you are likely dealing with a covalent compound. If, however, you have a metal and a nonmetal, one side of the zigzag versus the other side of the zigzag, then you are likely having an ionic compound. All right, so why don't we practice this? Return to, it should be chapter 4, not chapter 6, on your in-class assignment, and let's work questions 6 through 7 now. Again, feel free to work with a partner or write down any questions or challenges you may have and reach out to me via email or ask me the next time we see each other in class. All right, pause, and then when you're ready, resume. All right, so just to remind you, I will provide this flow chart for you. It's on Canvas, but I will also laminate it and give it to you in class. I may have already given it to you. And so this is a very handy flow chart that you can use to help remind you about how we name ionic compounds versus covalent compounds. It also gives you the hints to recognize whether it's ionic or covalent in the molecular, and then how we use the naming, when we need Roman numerals, when we need numerical prefixes, and when we don't need numerical prefixes. All right, so again, utilize this as you work through your homework and the in-class questions. All right, so when we talk about covalent bonds, we also need to talk about bond polarity. So, bond polarity is when the electrons between two atoms are not necessarily equally shared. And this has to do with the fact that some atoms are a little more greedy with their electrons than other atoms. So what do I mean by greedy? Well, when I say greedy, basically what I'm talking about is electronegativity. So the electronegativity of an atom is its ability to attract the shared electrons in a chemical bond. It increases from left to right, going across the periodic table, and increases from bottom up. So basically, if you were to draw a diagonal from cesium to fluorine, you would increase in your electronegativity. Notice these values here of 1.0 versus 4.0. That is your relative degree of electronegativity. Typically, electronegativity is high for our nonmetals, with fluorine being the most electronegative atom in the periodic table. And it is low for metals such as lithium, sodium, potassium, right? You can see we have very low numbers in terms of electronegativity here. Note, what is absent? Our noble gases here have no relationship with electronegativity because they do not participate in covalent bonds, right? Or ionic bonds. They don't really care to interact because they already have their octets satisfied. They really don't need any additional electrons. So bond polarity can be defined as the difference in electronegativity of bonding atoms in order to help predict how polar the bond is, right? So if you have one atom that is highly electronegative compared to another atom that is not, the electrons are going to be attracted to the more electronegative atom and away from the less electronegative atom. And it's not quite an ionic bond, right? The electrons are still existing between the two nuclei. We haven't given it up, but they are more likely to be around the chlorine than they are, say, this hydrogen. Now, anytime you have a diatomic, such as H2 or dihydrogen, the electrons are always going to be shared equally, and the bond is considered nonpolar, right? Because if you have two atoms that are the same, sharing electrons, they are going to have the same electronegativity regardless, so the electrons are going to feel the pull between the nuclei of both atoms equally. Again, we would call these bonds nonpolar. However, in molecules such as hydrochloric acid, the electrons are shared unequally because chlorine is much more electronegative than hydrogen, and therefore you are going to end up with what we call a polar bond. So if we look, hydrogen's electron is going to be pulled closer to the nuclei of chlorine because chlorine is greedier. It's going to pull those electrons toward it more often. And we're going to end up then with what we call a dipole moment, or an unequal distribution of electrons, where we're going to have more electrons around chlorine, giving chlorine a partially negative charge, and less electrons around hydrogen, exposing some of hydrogen's positive nuclei, so we have a partial positive charge. Now, these aren't formal charges like we see in ionic compounds. They're partial charges, so they're kind of temporary. They're not always there because these electrons are always moving, but statistically speaking, they tend to hang out here with the chlorine more than the hydrogen. So how can we predict how much electronegativity is needed, or difference in electronegativity is needed in order for a bond to be polar? So we can use our electronegativity values that are given to us in this table, and yes, you'll be provided this on the test, in order to predict bond polarity. So for example, if our electronegativity difference between the two atoms in the covalent bond is less than 0.5, then we would say that those atoms are equivalent in their electronegativity, and therefore we have a non-polar covalent bond. However, if the electronegativity difference between the two atoms is between 0.5 and 2.0, then we say that it is polar covalent. So for example, if we take chloride, which is 3.0, minus hydrogen's 2.1, we are going to end up with a value of 1.9, which is between these two values. Therefore, we would define it as polar covalent. If our electronegativity difference is greater than 2, well, then that's just really large, and you're going to end up actually creating an ionic bond. So those electrons will not be shared between the two nuclei, even not shared unequally. They are just completely given up. So for example, again, if we take sodium versus chloride, we have 0.9 versus 3.0. Now we're going to end up with an electronegativity difference of 2.1, which is greater than 2.0. Therefore, we say it is ionic. So the dipoles that are created, again, a polar covalent bond becomes more polar as the electronegativity difference increases. The separation of charges in a polar bond is called a dipole moment, right? Dipole is in you have two different poles. The positive and negative ends of the dipole are located by using the lowercase Greek letter delta with a positive or negative charge and an arrow that points from the positive end towards the negative end of the dipole. And your more electronegative atom is going to end up with the negative dipole. So we can look at these electronegativity difference if we look at electron density maps between the two atoms within a covalent bond. So again, if we have nonpolar covalent with an electronegativity difference of 0 to 0.4, you can see here that our electrons in this electron density map are shared pretty evenly across the two atoms that are in that covalent bond. However, if we have a larger electronegativity difference, in this example, they're saying 0.5 to 1.8. The other example said 0.5 to 2.0. Obviously, there is arguments in existence between chemists as to what is our cutoff, but basically 0.5 to 2. If you have that large of electronegativity difference, then we verge onto polar covalent. And again, you can visualize that unequal distribution as the electrons shift closer to our negative or more electronegative atom versus the positive end of our dipole moment. And then finally, if we're at 2 and higher, then we are creating an ionic bond. The electrons are no longer shared and they're transferred. And you can actually see that, right, where there is actually space now between the nuclei of the two atoms in this ionic bond. And we also see that we no longer have the partial charge as demonstrated by that delta symbol. Now we just have a true formal positive and negative as the electrons were given up from this atom and given to the more electronegative atom. So let's practice this concept. Please return to masteringchemistry.com and work question 8. Again, feel free to work with a partner, jot down any questions you may have, and bring them with you the next time we meet, or email them to me. Okay, pause, and when you're ready, resume the lecture. All right, so let's take a moment and now talk about Lewis dot structures, because Lewis dot structures is an awesome way for us to symbolically represent how many atoms are going to bond to another atom in a covalent bond, and whether we're going to have what's called single bonds, double bonds, or triple bonds between the atoms in a molecular compound. So we've already done Lewis dot structures or Lewis dot symbols for individual atoms. Now we're going to create Lewis dot structures for molecular compounds. So in a Lewis dot structure, a molecule is represented by a Lewis structure in which the valence electrons of all the atoms are arranged in order to give an octet. So for example, we can see the Lewis dot structures for methane, CH4, for ammonia, NH3, and for water, H2O. All right, again, you'll notice a few differences in these different models. Here we can see the individual electrons that are shared between each hydrogen and the central carbon. Or we can use a straight line to represent a single covalent bond that exists between the hydrogens and the central carbon. And what you'll notice is that this single line, each line will represent a pair of shared electrons. Here we are representing the shared electrons through the single line to represent a single bond, and an unshared pair of electrons that exists solely on the nitrogen, or two pairs of electrons that exist on oxygen. From these Lewis dot structures, we can then actually create three-dimensional representations of what these molecules might look like, which will then help us later on to predict the physical and chemical properties of molecules. We won't get into this part of the lecture until part 3. All right, so for right now, let's focus on how can we derive the Lewis structure. So, the shared electrons or bonding pairs are shown as two dots or a single line between atoms, as I already said. The non-bonding pairs or lone pairs of electrons are then placed outside of the atoms. Okay, so for example, with ammonia, NH3, we'll see that we have 3 bonding pairs of electrons, each between the central nitrogen and one of the hydrogens. And we also have a lone pair of electrons that exists on nitrogen. Note, there's no lone pairs on these hydrogens. Remember, hydrogen only has a 1s orbital, so it only has 2 electrons and therefore only needs 2 electrons to satisfy its quote-unquote octet. Technically, we call that the duet rule. But if you look at nitrogen, if each line represents a pair of electrons, then we have 1, 2, 3, 4, 5, 6 shared electrons or bonding electrons, plus the 2 lone pairs gives us a total of 8 valence electrons that nitrogen sees through sharing and its lone pairs. Therefore, nitrogen's octet is happy. So, how do we draw Lewis dot structures in 4 easy steps? Step 1, count the total number of valence electrons that are given for each atom in the molecular compound. Add 1 electron for each negative charge and subtract 1 electron for each positive charge. Step 2, draw the skeletal structure of the compound, showing what atoms are bonded to each other. Put the least electronegative element in the center or draw in the order that the formula is given. Then, complete an octet for all the peripheral atoms except hydrogen, aluminum, boron, beryllium. There's some weird rules here. Hydrogen we know because it's just the duet. Start with the most electronegative atom first until you run out of electrons. So again, if your least electronegative element is in the center, then your most electronegative elements are usually going to be on the peripheral. If we're dealing with a diatomic, it really doesn't matter which one you start with, just start with one of them. If there are not enough electrons to satisfy the octet for all elements, then we begin shifting electrons to form double and triple bonds on the central atom as needed, right? So for example, we have fluorine. If we're trying to create difluorine, each fluorine atom has 7 valence electrons for a total of 14. They can come together and share 1 electron each between them to create a single bond. And then we can count 1, 2, 3, 4, 5, 6, 7, 8. This fluorine is happy. 1, 2, 3, 4, 5, 6, 7, 8. Our second fluorine is happy. Both have their octet satisfied, and we are done. We can write this as F2, or our Lewis dot structure would look like this guy. All right. Now what about double and triple bonds? So a double bond occurs when atoms share 2 pairs of electrons instead of 1. This often forms when there's not enough electrons to complete the octet on the central atom or one of the peripheral atoms. So for example, if we look at carbon dioxide, we would find out that the Lewis dot structure for CO2 looks like this, where this oxygen is seeing 1, 2, 3, 4, 5, 6, 7, 8 electrons. The central carbon is seeing 1, 2, 3, 4, 5, 6, 7, 8 electrons, and then the other oxygen 1, 2, 3, 4, 5, 6, 7, 8. Now because we have 2 pairs here and 2 pairs here, we would designate this as double bonds on both sides of the carbon between carbon and oxygen. Sometimes we have to do a triple bond. This is when we're going to share 3 pairs of electrons, and again we can designate that as 3 straight lines. Again, this is going to happen if even after forming a double bond there's still not quite enough electrons. We will have to form a triple bond. Note, remember, hydrogen only needs 2 electrons. It will only form 1 single bond. If you end up putting double bonds and triple bonds between anything in hydrogen, it is going to be wrong. Take a step back and reassess. If you have to shift electrons around in order to satisfy carbon's octet, do not do it between carbon and hydrogen. Hydrogen has nothing else to shift. It's got to be between carbon and another atom. All right, so let's practice this by drawing the Lewis dot structure for phosphorus trichloride. So, step 1, count the total number of valence electrons that each atom contributes to the molecule. Again, remember, if you have a charge here, add 1 for each negative and subtract 1 for each positive. So, phosphorus being a group 5A element is going to give 5 valence electrons. Chloride is a group 7A element, so each chloride is going to contribute 7 electrons. Do not forget to multiply by the number of each atom. So we have 1 phosphorus, 1 times 5 gives 5. We have 3 chlorides, 3 times 7 gives 21. There's no charges here, so it's 5 plus 21 gives us 26 total valence electrons. Next, draw a skeletal structure of the compound showing what atoms are bonded to each other. Put the least electronegative element in the center, right? So if we go back to our electronegativity table, you should see that phosphorus is going to be less electronegative than chloride, so we put phosphorus in the middle and we surround it with chlorides. All right? Sometimes when it's hard to assess, you may just draw in the order that the formula is given, right? So it's P is first, then Cl3. So P would go in the middle. Next, complete an octet for all the atoms, starting with the most electronegative atom first. So we're going to start with the chlorides. They're more electronegative. It really doesn't matter which one you start with first. So what I do is I put 8 around this chloride, and this chloride. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That's going to give me 8 times 3, which is 24 electrons. Again, my total number of valence electrons is 26. So the two remaining electrons will be put on phosphorus. So now we can satisfy phosphorus's octet. Now you're going to take a step back and count to see if everybody's octet is happy. So chloride, we can already see, has 8. This chloride has 8. This chloride has 8. Phosphorus has 1, 2, 3, 4, 5, 6, 7, 8. So phosphorus is also happy. All the atoms, therefore, have the octet, and there are no remaining electrons, so there is no need to rearrange anything. So smiley face, yay. Exceptions to the octet. So while the octet rule is useful, please remember there are exceptions. Again, hydrogen only requires 2 electrons in order to satisfy its duet rule. Nonmetals such as phosphorus, sulfur, chloride, bromide, and iodine can actually form compounds with 10 or 12 valence electrons. We're usually not going to have to worry about this. I'm not going to give y'all anything super complicated to do a Lewis dot structure on. The sulfur atom has an octet in many compounds, but in SF6, we actually can have 12 valence electrons for 6 bonds. So again, this is just important to note. The hydrogen rule is the one you are going to use the most. We're really not going to touch on these, but I just want to make you aware that rules are often broken. So, your turn. Get out a piece of paper and start working on drawing the Lewis dot structures for these following compounds. Again, the next time we meet in class, we can go over these if you still have questions. Many of these you can also check your answers by looking them up online, but try to do it on your own first. Remember, go back to our rules, 1, 2, 3, 4, in order to draw these Lewis dot structures. Right? Let's see. Okay, once you've done it on paper, you can also test yourself. Go to masteringchemistry.com, open chapter 4, and try question 9. And try to do question 10 on your own. Question 10, it's really going to help you to draw the Lewis dot structure out on paper first, and then do it in Pearson. All right, so work questions 9 and 10. All right, so when we come back for our 3rd installment of this lecture series, we will now take Lewis dot structures and help predict molecular shapes in order to then predict how these molecules will interact with each other and their chemical and physical properties. All right, so I hope you guys have a great rest of your day, and let me know if you have any questions about any of the examples that we worked, the guided practices, or the mastering chemistry questions. All right, I hope you guys all have a fantastic day. Bye.